That's section 5.2. What is that I'm doing in that 5 part 2? Took a sample. And then I'm asking about the mean. So therefore, what needed to change? Standard deviation. I love it. So this one was all about figuring out what the new standard deviation is. Some of you guys figured it out and then circled it and kept going. Telling me what the new standard deviation is doesn't answer the probability question, right? You still had to go make a z-score, look up the area like always. You just use the new standard deviation. All right. So whatever this new standard deviation is. Another way to answer 5.2c would be to figure out what the max and min usual values would be, right? I like it. So you could have went mu plus or minus 2 of these. Because now I'm talking about a group of 6. I can't use the old standard deviation. I must use the new one. You guys semi with me here. So if I'm talking about a group of 5 or 6, I can't use this to describe that situation. I must use the new standard deviation. So a few of you guys did this. This was not the only way, like I said. You could have said, well, 5.2b basically said it was impossible. It happened. Some assumption must have changed. Something that in the past must have changed. The average temperature might have gone up or something. Okay, maybe. You guys all right with this so far, you guys? So this is basically this formula. Just right here, I put the new standard deviation because I'm talking about a group of scores, not just an individual temperature in this case. Okay, maybe. All right. What we're doing today is taking a lot of the stuff we've already done, and in that problem, I pushed it a little bit closer. Being attacked from both sides. So what we're doing today, this is chapter 8. So I need to attack this from a few different directions. So I'm going to start with the situation that's kind of old news, and then kind of bring in what's new. So if I told you the mean was 50 and the standard deviation is 4.5 for some situation, I take a sample of, what you got, Jeff? 38 things. Highly descriptive problem. When you're working with things. Can you tell me between what two values would I find 95% of all sample means? Okay, let's build this up, right? So I want to find between what two values lies 95% of all sample means of size 38. Okay, this is old news, believe it or not. Semi-old. This piece here should sound very familiar. We've done problems like this before, right? What bounds the middle 95%? We can figure that out in terms of z-scores right now. How far out, how many standard deviations would I go to capture 95%? Be careful. We can be a little more precise now. I appreciate that, because that used to be, we just said 2 to make it easy, to be honest. If I use a z-score chart, it could be a little more precise. So can you guys look up right now? Don't say it out loud yet. Can you figure out what two z-scores bound the middle 95%? We've done that problem before. Did I bring any z-score charts? No. Maybe.
Yes.
If anybody needs one. Say again? Yeah, so what's this going to be? Negative 1.96, and this will be positive 1.96. Okay, I like it. Good. By the way, just a little teaser in the middle of this. We are about to get into learning where the shit that plus or minus 4% you see. Have you ever seen, has anybody ever seen, heard, been told, 40% of people want to vote for candidate A, 42% want to vote for candidate B, and at the bottom there's plus or minus 4%. It wasn't just like, I'm not sure, man. Plus or minus what, 4? Let's cover our ass, because I don't know. Shit. That actually comes from a formula. We're going to develop it. We're starting to develop that formula right now. What should make sense is, the bigger my sample is, what should happen to that plus or minus 4% number? It should get smaller, because the bigger my sample is, the more sure I should be about what I see. Okay, maybe. I love you guys. All right. So, what do we got so far? So now, how in the world, now I've got this. What else do I need for this formula? So I'm going to use this formula basically, but what's going to change about this formula? I can't really use that one. What's got to change? What's got to change? Standard deviation. I like it. So I got to change it because I'm not talking about individuals anymore. I'm talking about groups of 38. So to be honest, the formula is actually this now. Is that cool? You guys see that? It's the same dumb formula. It's just I got to use the right spread. Okay, I like it. Maybe. And let me make one more tweak. If I was going to do a bunch of problems like this, and one problem said 95% confident, or 90, I'm sorry, I used the word too early. One problem said 95%, capture 95%, and another one said capture 90%, and another one said capture 99%. Isn't it always going to be negative number, positive number, right? So let's change one more thing about this formula. Let's make it plus or minus. Because I'm going to go up so much and down so much. Does everybody follow the reasoning behind that? Every step should make sense. I have to change the standard deviation. This is just me going, let me capture the idea going up and down, let me just put that idea in there, just so I don't forget. Right, nothing wrong with that. Okay, so let's figure this out. Do I have everything I need? Yes. What was the mean? 50, give or take 1.96 times 4.5 divided by the square root of 38. This is almost what chapter 8 is all about. There's one kind of large tweak we got to make to this formula yet. Let me say it too. It's large conceptually, very small in practice. Okay, I like it. So this formula, let me put it over here. This is a tiny computational thing, but what piece of this should I probably figure out first? What kind of makes sense? I'm going to figure out this piece. Right? I mean, sort of. You don't have to, but it kind of makes sense. Let me figure out what the hell I'm adding, subtracting first. So help me out with that. What do you come out with that? I have some calculators too up here if you need to borrow one. Anybody getting anything? You guys getting any number for this? Yes.
Not that I think it really matters, but 1.96 isn't right.
Why?
Because it's 0.9750.
Oh, I can't believe I. Wait. No, it's 1.96. Yeah.
Can you explain this to me?
Yeah. So what percentage is in here? No. If there was 0.5 there, what would be there?
2.5.
If you look up 0.025, you'll get negative 1.96. Yeah. You got me worried there. By the way, let me point this out. You're not always going to be able to. You guys, everybody have your z-score chart? Look at the positive z-score side in the bottom right-hand corner. Do you see anything that relates to this problem we're doing? 95% relates to 1.96. I mean, those are like the three most common intervals to create. And these problems, they are called confidence intervals. And the next step is to understand why they're called that. So that's what I call the baby chart. Real quick place. Now, of course, your teacher, you know me. I'm going to say create a 93% interval. And oh, that's too bad. You got to remember how the hell to do that. Okay. I like it. So let's see. What I get this just because I don't see anybody help me out.
1.43.
Yeah. 07, blah, blah, blah. Right? So then I love it. I haven't had this in a long time, but I remember before I had somebody ask me where that button was. So 50 minus 1.43 and 50 plus 1.43. Those are the two things, the two values that capture 95%. So how confident would I be that a sample of 38 things would be captured by this interval? Yeah, because what percentage of all samples are captured by this? 95%. So how confident am I that this interval catches some certain number, 95%? Please let that make sense. This thing captures 95%. So if I don't like fish. I like to fish, but I don't like to eat fish. They taste horrible. But if I threw a net out and I wanted to catch a certain type of fish, and my net catches 95% of all the fish, everybody else is like, what the shit, man? How confident am I that I caught the fish? 95 frickin' percent, right? So this interval catches 95%. So how confident am I that it catches a certain value? 95% confident. Okay, I like it. Okay. So, this is semi-old news. The only real tweak is this, and that's not even really new news. I know that has to happen when I take a sample. Okay. So, here's the real new thing. In statistics, when I go to study something, do I know this? If I'm like, I wonder how many, or, what's the average? This, I have no idea what that is, right? Now, yeah. So, the real picture is we normally don't know a flippin' thing. We normally don't know mu, and we normally don't know sigma. We don't know shit, right? So if I take a sample, can I figure out what mu is? What's mu represent? What's that symbol mean? The mean of the population. So can I figure out what mu is and what sigma is from a sample? No. What can I get from a sample? What's the symbol for me for a sample? S bar. And what's the symbol for standard deviation of a sample? S. All right. So X bar is an estimate for mu. If you took a sample of 90 Grossmont students, completely randomly selected, and you get a certain average age, you feel pretty good that's the real average age. Right? That's X bar, but it's a good approximation for mu. Same thing with S. It's a decent approximation for sigma, the larger the sample, then the more random it is. Okay, I like it. So, the first step we take is getting closer to honest with the way statistics normally works. But let me show you why it isn't completely dishonest. Okay. So there's going to be a situation where we're going to take a sample. Sigma is known. Calculate X bar. I like it. So the reason this works, and the reason that this is okay, is because, for example, let's say there's a known average life expectancy. We've seen that before, right? Or there's a known standard deviation of life expectancy, too, right? We know what the standard deviation is in life expectancy. So I go to a town where everybody seems to be living really long. So I take an average, but I know the standard deviation of everybody. So for any subgroup of that population, that is still the standard deviation. You guys kind of with me? I'm curious to find out, like, for these people in this town, right? If I figured out what it was, what they eat or whatever, if I figured out what it was that was making them live longer, what would that do if I applied it to everybody? It's got to be a better way to say this. So if I really want to figure out, are these people truly different from the rest of the United States? One basic way to do that is to create a confidence interval and then see if that whole interval is above the mean of everybody else. That would be evidence that their mean is actually higher than everybody else. So a slightly better situation. I didn't want to use this one. It's the only one I can think of. Say there's dolphins, and there's an average length of all dolphins, right? And then you go and you take a sample of dolphins in a certain area. Can you get the entire population of all the dolphins that live in some certain area? That would be really difficult, right? There's no way to be certain. So you're going to have to get a sample of dolphins. You know what the standard deviation of all dolphin lengths are. You're kind of assuming that that's known. I want to see their average and see if there's any evidence that they really are different. Maybe there's different food in the area, something. Okay. So here's the nifty thing. There's an actual average length of those dolphins that exists, right? If I take a sample of dolphins, will X bar necessarily equal mu? In fact, I would put money on it being different. You with me? Okay. So I'm going to take a sample, and it's going to show up somewhere. Now, if I create an interval around that sample mean, so if I make like a 95% confidence interval, how confident will I be that my interval catches the real mean? 95% confident. I like it. And what that really means is somebody else could come along, the red team can come along, get their own sample of dolphins, get their own sample mean, create an interval, and maybe they actually don't capture the real mean, but they don't know. We don't know what the real mean is. So if I'm 95% confident, what that really means is 95% of all intervals that are created will capture this. 5% won't. Okay. So, what I changed, the one thing left to change in this dude here is to replace this with our best guess. Make this X bar. So this is how you construct a confidence interval for a mean. Okay, so let's do an example. And then once I got an example, I can probably explain better what it means. You're going to have to write a paragraph at the end of these problems, which is always exciting to hear. All right, let's try this problem. So if I know, let's know that the standard deviation of grades is 17.14. We take a sample of 41 grades. We'll find the sample mean of, which gotcha, 74.9. So what we couldn't do before, what we're trying to develop now, is how to better reflect the fact we know this isn't right. Is this going to be the average for everybody? No, but it should be close. So really the whole idea of this is, how do I capture the idea of close? So once I say 74.9 and I figure out how far to go down and how far to go up, to catch like 95% of all the grades, I can say the actual average would be captured by this interval I just created with 95% confidence in that case. So if I'm like, let's construct a 95%, I'm going to call it CI for confidence interval. And these problems, they're very prescriptive, almost like everything we do. I kind of try to show you the progression of how we changed this formula that we've known for a long time. We changed it into this now to fit the situation we're in. We don't know the mu. Our best guess is the sample mean we got. We had to take a sample, so I got to change the standard deviation. And I want to capture the middle whatever percent, and that's where the plus or minus piece came in. So the only thing I don't know at the moment to plug into this formula is what? What do I not have? We kind of know it because we just figured it out, but what is it that I don't tell you? The z-score. And where do you get the z-score from? How confident you want to be, because that controls how far out you go. So we just figured out the z-score is 1.96 for this, right? I like it. And now it's really just a plug and chug problem. I know x bar, give or take this many steps. So if I start at my guess, my best guess is the sample mean that I see. And I go out from it this much, I will end up being 95% confident that my interval has the real mean in it, because I'm 95% confident my interval has anything in it. It's got 95% of everything in it. I like it. This piece, hopefully this makes sense. Sometimes math people give good names to things. That's the error, because that's how far off I think I am. It's this, give or take that. So this piece is called the error. And I always suggest to people to calculate that first. Yes?
Do we always have the same percentage?
No. I just use 95 right now because we already looked up the z-score. Yeah. Like I told you, I can make it 90, 98, 99, 82, whatever the hell I feel like. The most commonly used one is this, which relates to why 2 was the most commonly idea of where unusual starts, 2 standard deviations, because it's just rounding 1.96. I like it. So anybody going to help me out? What's this come out to be, this piece? Let me put it up here.
5.25?
5.25?
Yeah.
I don't hear any objections, so I'm going to go with that. Okay. So in general, the error, you should take it out one more decimal place than your mean. So that's beautifully done. And now you just subtract it, add it. 69.65. And then 70, what is that going to be? 80.15.
Yeah.
So that's what we did earlier. The only difference between what we just did now and the one that we made earlier is this one we're being a little more honest and saying, I don't know what the flip mu is, so I got to use my next best guess, x bar. That is a flaw in this, because this isn't really the true middle, right? So confidence intervals really just give us a better idea about the relative certainty we have with this. So if you look at this interval, would you say for grades, I think that was what this was, right? Would you say for grades, is that pretty narrow or pretty wide interval? It goes from D plus to B minus, right? So that's kind of wide. So this is really showing us in this situation, we're not terribly certain about. If I just say this, that kind of is giving the idea that, yeah, it's 75, it's about 75. This gives a much better, oh shit, you really don't know too well. And what is one of the main reasons why that interval came out so big? There's kind of two answers I would accept here. What was it that should make the error get smaller if I take a...
Larger sample.
And the sample is 41. That's not very big, right? It is big enough to do what?
Be normal now.
It's normal. That's why I could do any of this shit, right? I want to point that out. If that would have been 21, you couldn't have done any of this unless it said it was normal somewhere. I like it. So that interval gives us a lot more immediate information about how certain we are about this. Now, the next level thing you can do, for a different class, if I got this interval of grades, what you got, Jeff? If that was the interval for a different class, what is this evidence between the two classes? Can anybody figure out what evidence have I showed between these two classes? Would you say that the means of these two classes are the same? This is evidence they aren't the same. Why? Because the intervals don't overlap. Maybe. So confidence intervals, the main reason they exist is just to give immediate measurement for somebody to see how certain they were about what they found. That is not very certain. The next level is to do very basic checking of claims. If I claim that the average was the same, this would be evidence that I'm wrong. Why is it not proof that I'm wrong?
You're only 95%.
Because I'm only 95% sure about either one of these things. Yeah. But still, that's really good evidence. I love it.
So, does that mean overall that you have less than a 95% certainty that they don't overlap because it's 95% on either one?
Yes, so you can get into the more technical details about which side it's on and all that kind of stuff, right?
Right.
Yes, I like it.
Just a straight multiplication across
Multiplication of...
of 0.95 and 0.95.
Oh! There's a lot that goes into considerations about what you're talking about. Because this could be shifted up or shifted down. We're not sure exactly where this true center is. And there's a lot that goes into that. So just on the surface of this, since these don't overlap, with 95% confidence, I can say that this is evidence the means are different. Confidence intervals aren't good enough to really fully investigate a claim because they're built on something that really is in the middle. So chapter 9 is called hypothesis testing. And that's what you use to like if you have a new drug and you want to show that it's better than some old drug, the clinical trials you do, that's what you use, the stuff in there. This is very quick and it just gives us a general sense of where things stand. Okay. All right. One last thing before I'm going to give you this handout to try on your own. Let's see. Yeah, Let's keep that up there. So this formula, this piece of this formula is the error, right? So the error is this. If I took a larger sample, what would happen to the error, of course? Go down. It would get less, which makes sense conceptually. The larger the sample, the more sure I am about what I see, so the less error there should be. And it makes sense mathematically, because I'm dividing by a bigger number. Ooh, so that should get smaller. Are you guys with me? So it's always nice when the math matches with the conceptual idea. I like it. So what I can do with this now is, before I even do a confidence interval, let's say that I knew how close I wanted to be. So that interval we created was really pretty bad, right? You guys kind of agree with me? It went from, like I said, D minus up to B plus, or B minus. D plus to B minus. That was a pretty wide interval. So what if I said, how many students would I have to take, how many grades would I have to sample to be within so much? How small do you want your interval to be? How small do you want your error to be? What do you think? It was, what did it come out to be? I can't remember. 5.25. That's kind of big, right? It's like a full letter grade, 10.5. So let's say I want it to be 2. Does that sound right? So I want to be within 2. So this is what I call a feasibility study. So I'm going to say, I want my error to be 2. How large of a sample would I have to take to get there, right? So what's kind of wrong algebraically about this equation? If I want to know what n is, this equation isn't solved for n. How do I solve this equation for n? Take a minute and solve this equation for n.
Is it still on the 95% confidence interval?
Say again?
Is it still on the 95%?
At the moment, I don't care. It's just an equation I want you to solve for n. And yes, we will bring that 95 back in. But right now, just solve that for n. One of the most useful, no, don't get me wrong, I'm a math teacher, so I think all of algebra is frickin' useful. Doesn't matter what you think, it's just true. But one of the most useful little tiny things from algebra is, if I'm trying to solve for a variable that's on the bottom, I could just switch this and this, just switch. Now, it's not magic, it's how would I, what's wrong with it being on the bottom? Oh, it's on the bottom, it sucks. So I'm going to multiply by square root of n, and then I'm going to divide by e. Won't those just switch then? Right? And what is 10 divided by 2? But if I switch these, is it still true? Well, frickin' of course. If you divide by 10 by one piece, you get the other piece. So I can just switch the pieces, and it still has to be true. So I get square root of n equals z sigma over e, and then what do I have to do the last thing? Square. So here's the formula. If I want to know how big of a sample I need, that's the formula I use. So if you see a question that says, how many people would we have to sample, or how many things would we have to take, or whatever, to be within so much, I want to know the sample size, I'm going to use this formula right there. So in this case, what do we say? How many, oh shit, let me not erase too much. Yeah, okay. N was 41, okay. So to be within 2. How many do I have to take? They're not always going to use this word, but the word within is a true key. That's the error. That's how much I'm within something. So I'm going to have n equals, z was 1.96, sigma is 17.14, and my error, I want to be within 2. So whatever that comes out to be. I think it's like 289. What is it? 282? Yeah, 282.1459. Is everybody getting that okay? You got to do all this and then square it.